Hi, my name is Clayton MacArthur, and I am the president of TrickFire Robotics based out of the University of Washington, Bothell. We are comprised of 100 plus members, including an engineering and business division. This year, we have put an emphasis on community outreach and campus involvement. We have hosted several campus-wide events and visited local school districts to encourage future participation in robotics. This year, we have a new chassis that is a welded aluminum frame that minimizes hardware use and brings our weight down. We are using our old rocker bogie system that allows for even weight distribution across the chassis, and this rocker bogie system attaches to our drive-based system, which is 6 RMD X8 motors that have custom TPU printed wheels that have paddle tread that allow us to go over sandy terrain. Along with the rocker bogie system, this performs well on most terrains.
The power system has been updated from last year's URC with an increased focus on modularity. The 48-volt battery feeds into a fuse, e-stop, solenoid, and into the new e-box. The e-box allows us to install and remove components with ease. The e-box has the ORN computer, stacked PCBs, PoE injector, and GPS module. Communication between motors and the ORN is accomplished with daisy-chained CAN lines. The rover is being controlled through a router while the software between mission control is being developed. We use an antenna with impedance matching operating at 315 megahertz. Once developed, we will achieve remote control of our rover through our Mission Control website. Mission Control interfaces with the rover via WebSocket so that we can both control the rover and read critical telemetry data during operation.
The autonomous navigation system uses advanced navigation, localization, and computer vision techniques to fulfill its mission. The Z2i camera on the front of the rover collects data for a NAV2 global and local cost map. This is handed to a custom global navigation node using an A-star search algorithm. This node produces a path for the NAV2 local planner to execute. The rover localizes itself using odometry data from the wheels, IMU data from the Z2i camera, and GPS data from the onboard GPS module on the front of the rover. These inputs are fused together via an EKF column to provide the rover with accurate positional data. Once the rover has navigated to the goal coordinates, it finds the Uruco tags using OpenCV and detects objects using YOLO object detection.
This year, we redesigned the arm. We kept the previous year's geometry with actuation for the turntable, shoulder, elbow, wrist differential with twin axis rotation, and grabber. However, this year's arm's weight was reduced by about half. Our design achieves durability and lightness through carbon fiber tubing for the bicep and forearm linkages. We use BLDC motors for the turntable, shoulder, and wrist differential, and a linear actuator for the elbow joint. The gripper is reused from last year and features grippy TPU pads and a worm gear reduction mechanism powered by a continuous rotation servo to prevent backdriving while lifting heavy loads. We control the arm using inverse kinematics to achieve maneuverability and ease of control in both teleoperation and autonomous modes.
The linear actuator of the auger is driven up and down through a rotating lead screw to dig into the soil. The sample is then raised up to the remaining science module. Lead screw actuation allows us to have a greater clearance under the rover during transit, as well as making the system more resistant to dust. Once the soil is raised, the sample is forced out of the auger to fall into the testing chamber, which contains our life detection method, the CO2 sensor. Real-time data communication is done through the on-rover computer where we can set baselines for different trials and analyze the rate of change in CO2 levels. The sample caching mechanism rotates using a servo motor to line up our storage tubes with the testing chamber to create an O-ring sealed testing environment. After testing has been completed, the sample caching system then rotates and constricts the top of the storage tube with a rubber seal and places the next storage tube in place for collection.
Thanks for watching our systems acceptance review. I want to say a huge thank you to our faculty and sponsor support. See you in Utah.